start the recording and share my screen, and we can get started. Share. All right. And maybe I can also pull the chat out. So if you want to chat, you can. And it's just kind of never know where to put these things. Let me just minimize it. Okay, here. All right, so, I mean, I've got something prepared, but before I start talking, I want to ask all of you, you have questions, comments? Did you have a chance to look at the video on Unit 8? Is there something in particular you'd like me to address?
So I didn't get all the way through the video,
Mm-hmm.
but I was a little bit confused about the difference between an equivalence relation and equivalence class.
Okay, good. We'll get to that. So I'll make sure to let me note it here. So difference between equivalence relation and equivalence class. Okay. I'm not going to start from this but we'll get there. So I noted it here so we don't forget. Any other questions, comments? Any questions, comments about Unit 7 that you might still?
I have something for that actually.
Yeah.
I was a little unsure of my answer on the homework to I think it was 7.4 relating n choose k to like a surjective function.
So yeah, so let's talk about that. That was kind of an interesting exercise. So let me illustrate that in a specific case, right? In the case of X being a set with 3 elements, say A, B, C, right? Then 7.4 told you, okay, you can give a function from the power set of X to the set 0, 1, 2, 3, right? And the definition, so F need to assign to a subset of X needs to assign a number that is either 0, 1, 2, or 3, and it assigns the number the cardinality of U. Okay, so let's see, what is the power set? Let's list the elements of the power set of X, right? There is the empty set, there's the singleton 1, the singleton 2, the singleton 3. There is the 2-element subset 1, 2, the 2-element subset 1, 3, and the 2-element subset 2, 3. And then finally, there is all of X, 1, 2, 3. And did I call them ABC, right? I'm such an idiot. Okay, sorry, let me fix this, actually. So it's not. These were supposed to be A's, B's, and C's. So A, B, C, A, B, A, C, and B, C, and A, B, C. Sorry. And this function assigns to each one of these subsets its cardinality. So it's going to assign 0 to the empty set. It's going to assign 1 to the singletons. It's going to assign 2 to the 2-element subsets, and going to assign 3 to the 3-element subset. Okay. So what is F inverse of 0? Well, it's just the empty set. F inverse of 1 is the set of subsets consisting of the 3 singletons. See? Sorry, this is F inverse of 1. F inverse of 2 consists of AB, BC, and AC. And F inverse of 3 just consists of X. Okay, so now the claim is that the cardinality of X, right, should be equal to the summation for Y in Y of the cardinality of F of the inverse image of each element Y, which in this case, you know, it should be the cardinality of F inverse of 0, right? Y can be 0, 1, 2, or 3, plus the cardinality of F inverse of 1, plus cardinality of F inverse of 2, plus the cardinality of F inverse of 3. Okay, but now we know what all of these cardinalities are. The cardinality of a power set of a set with 3 elements is 2 cubed, right? And the inverse image of 0 via this function is the number of subsets of a set with 3 elements with cardinality 0. So this is 3 choose 0. Similarly, the inverse image of 1 is the number, sorry, the cardinality of the inverse image of 1 is the number of 1 element subsets of a set with 3 elements. So there is 3 choose 1 of this. And similarly, there's 3 choose 2 elements in the inverse image of 2, and 3 choose 3 elements in the inverse image of 3. Okay. And so this is another way to prove that the sum of the binomial coefficients is equal to a power of 2. The sum of all the n choose k's, as k varies from 0 to n, is equal to 2 to the n. Okay, now what I've done here for 3, there's nothing special, right? With X being a set with 3 elements, you can repeat exactly the same argument if X is a set with n elements, and you'll get another proof that the sum of the binomial coefficients n choose k is equal to 2 to the n. Okay, did that clarify 7.4, Tyler?
Yeah, it did. I was with, like, I had gotten right up to the point where you have the sum of y and y, and then I just hadn't made that connection to the actual power set.
Okay,
So
great.
yeah, that makes sense.
All right, how do I shrink this thing now? Okay, great. Let me get chat box again. Hopefully it's small. No, big. Sometimes technology is crazy. Okay. While I fumble with technology, any other questions, comments, anything else you need to clarify? Okay, so I want to, before we start talking about section 8, I want to spend a second or two talking about the challenge problem in section 7, and yeah, 7.6, right? Which is essentially saying every function f from x to y can be decomposed as the composition of a surjective function and an injective function. Okay, so first of all, why do we care about a statement like this? Well, first of all, because being injective and being surjective is kind of nice, right? When we have the functions are injective or surjective, sometimes we can prove nice theorems about them. But if you have theorems that hold for injective and surjective functions, then that means that those theorems actually hold for every kind of function, right? Well, and these theorems respect composition of functions, right? They still hold with respect to composition, then they're true for every function, right? Because every function, no matter how ugly it is when you start, you can always write it. So let me repeat what I want to say here. You start from a function f from x to y, which might be very, very non-injective and non-surjective, and you can always break it down as a function f1 from some x to some z, and this f1 is injective, followed by a function f2 from z to y, and this function is surjective. Okay, by a quick chat typing, how many people find this fact surprising or not surprising? Type a quick yes and no and see let's see what happens. Surprising, yes, yes, yes. Okay, good. Well, so first of all, I'm glad that it's surprising because I remember the first time I encountered it, I was surprised, right? And the nice thing is that this is not just some weird theorem. It's actually a quite natural fact, but it comes from understanding functions well, right? So let me try to illustrate things with an example. So let's pick up a function which is neither injective nor surjective, where x and y are pretty small sets. Maybe x has two elements, a and b. Y also has two elements, smiley and frowny. And because I'm feeling optimistic today, the function f will send both a and b to smiley. Okay, so f is not injective and f is not surjective. Okay, but what I can do is the following. I can pretend this is calc 1, right, and say, okay, I'm going to write the elements a and b of x horizontally, and I'm going to write the elements frowny and smiley of y vertically. And then I can create, and again, let me draw the arrows here. This is exactly the same as I did before, right? B goes to smiley and A goes to smiley. But now what I can do is I can consider the graph of the function. And the graph of the function is a subset of x cross y, right? So here I have A frowny, B, oops, yes, B frowny, A smiley, and B smiley. Okay? And the graph of the function is this subset right here. But I have a natural function from x to the graph of x, which just sends every point x to the pair x comma f of x. Right? So let me call this function IG for inclusion into the graph, right? And this sends any point of x to the pair x f of x. Okay? And this function is always injective. Right? Why is it always injective? Well, because if x1 is different from x2, then the first entry of the pair, x1 f of x1 and x2 f of x2, their first entry is going to be different, and therefore the pairs are going to be different. Right? If one of the two entries of a pair is different, then the entry itself is different. Okay, but now, how do we get from x cross y into y? Well, we have also a very natural function, namely the projection function, pi2, right? So p2 from x cross y into y that sends every pair, little x comma little y, to the second element of the pair, well, this is surjective. Why? Because for every y in y, if you want to find an element that is mapped there, take whatever x you want as the first element of the pair, take that y as the second element, and then the image will be y. Okay? And now notice that what happens when you compose these two, if you follow the red arrows and then the purple arrows, well, then you get precisely the blue arrows, right? So if you look at the composition P2 of IG of x, well, this is P2 of the pair x comma f of x. Did I close enough parentheses? No, one more. And this is equal to the second element in this pair, so that's equal to f of x. Right? So the function, this is true for every x in x, for any input. P2 of IG of x is equal to f of x, which means that P2 composed with IG is equal to the function f as a function. Okay? So give me a quick yes or no via chat if it makes sense. Makes sense. Yes, 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 yes. Okay. Great. Okay. Thanks a lot for the feedback. Let's still a little confused. Okay, can you tell me more, or do you need some time to meditate on it? I'm gonna share these notes, and this lesson is gonna be recorded. So
I think that it's just because I didn't hear you correctly when you talked about the injective function, because I understand everything after that. I'm just lost on the injective function.
okay, yeah. So what I'm saying is that the function that sends any element of x to the element of x cross y, right? That it corresponds of the pair x comma f of x, right? This function is injective because if you start from an x1 which is different from x2, so for example, a and b, right, in this example, well, they're going to be sent to pairs such that the first element of the pair that a is sent to is a, and the first element of the pair that b is sent to is b. So if a is different from b, there's no way that the pair a, whatever you have there, can be equal to the pair b, whatever you have there, right? Because for two pairs to be equal, you need both entries to be the same. That help a little bit?
Yeah, that makes more sense. I didn't hear you when you did that.
Yeah, so A and B's are both the elements of X and the first entries of the pairs that they're assigned to by IG, right? So if A is different from B, then certainly the pairs that they're sent to are going to be different because their first entry is different. Cool. I hope silence means everything. So sounds good. Okay, great. So I want to start talking about Unit 8 now, but I want to go back again to some philosophy that we talked about in Unit 7, because I want to use that to motivate Unit 8, bizarrely enough. Let's see if I can shrink this. Okay, let's go away, let's open it later. So in Unit 7, in the group work, we saw that the concept of injective function and the concept of subset are in a certain way the same thing. And what do I mean by the same thing is that if you're given an injective function, if you start from an injective function, then what you can do is you can come up with a subset of y, namely the image of x via the injective function. So here in this picture, I have an injective function f, and I can just look at the image of f, and that determines a subset of y. But this subset of y is very closely related to x in the sense that the function f realizes a bijection between x and f of x, right? So if I start from an injective function, I get a subset of y and a bijection between x and this subset. Okay? So vice versa, if I start with a subset of y, now I don't have any function yet, I just pick y and a subset, then what I can do is I can construct an injective function simply because I can consider u as an abstract set out there, and I can construct this function iu that just assigns each element of u to itself, right? So this is showing me that if I start with an injective function, I can construct a subset of y. Vice versa, if I start with a subset of y, I can construct an injective function, right? So the notion of injective function as subsets are very, very intimately related, okay? Let me pull the chat out again and give me a quick yes, no, maybe. This making sense? So what we're doing is we're saying, okay, a subset is sort of an object of a set. A function is something more dynamic, something that relates sets, but subsets are the same of injective functions. Yes, no, maybe. Okay, yes, maybe. Okay. Yeah, so again, let me repeat what I think is cool and surprising here is that we think of subsets as objects, things with elements. We think of functions as rules, way of associating things, right? But somehow there is a way to, given a subset, to come up with an injective function, and a way, given injective functions, to come up with a subset. Okay. And so what I'd like to do, what I want to do in section 8 is to try to do the same thing for surjective functions, right? And things get quite a bit more complicated, okay? So let me go all the way down here. So in unit 8, we want to say, okay, so if injective functions are the same as subsets, then surjective functions are the same as what? Okay. And well, the answer is that is the same as quotient sets. And in order to understand what quotient sets are, we need to introduce and talk about the notion of equivalence relations. Okay, so let's set this goal. So this is our goal. Let's set this aside and we'll come back to this. Our goal is to really understand this part and what all of these things are. Okay, so first thing, there's many steps. Is partitions. And this is, in a sense, I think the easiest of these concepts. A partition is just a way of breaking up a set into disjoint subsets. Okay, so X is a set with some elements, and I decide somehow that I want to break it up into disjoint, non-empty subsets.
So this is a little bit confusing in the book. So disjoint means that there's no intersection, and then parentheses, like where you have in parentheses non-empty, like that's just like a clarification, correct?
Let me
Like
look at the
disjoint
book
doesn't
to make
mean
sure.
non-empty, I guess is what I'm asking. Or does it?
Well, let me make sure. Let me look at where I'm. Oh, when you say X alpha 1 intersect X alpha 2 is equal to empty, or? Oh, disjoint. Yeah, sorry. So non-empty, that's a very good point. No, when I say non-empty, I mean that I don't want to take the empty set as a subset, right? So in principle, you could do like, okay, I'm going to take this U5 to be the empty set, right? And it's still the case that U1, union U2, union U3, union U4, union U5 is X, and that any two of them do not intersect. But I want to forbid this. I don't want to. I don't want you to allow you to take the empty set. Okay? So this is not going to be allowed. All the subset that I'm going to break up X into are going to be subsets that have elements, right? So let me write down here. So all UIs have elements. No two of them intersect. And their union is O of X. Okay? Thanks for that. That was a really good observation. Thanks, Berkeley. Okay, everybody happy with partitions? Yes. Okay, great. So thanks, Heidi and Vanessa. So let's go then B to equivalence relations. So an equivalence relation is a rule, right? So this is kind of like a function is a way to assign to every input and output. An equivalence relation is a way to decide, given two elements of a set, whether we consider them equivalent or not. Okay? And given a set, X, I mean, an equivalence relation on the elements of X is not something which is God-given, and it's not something which there's only one of. I mean, one can put, in general, a ton of equivalence relations. One can come out with many, many different rules that are gonna, be called equivalence relations. And if you have different rules, then they're different equivalence relations. Just how you can have many different functions from the same input set to the same output set, right? You can have many different equivalence relations. Okay, so then you could say, well, then can I just kind of flip a coin? Every time two elements come up to me and ask me, are we equivalent? I flip a coin, and if it's heads, I say yes, and if it's tails, I say no. And no, you cannot do that, right? If you decide when elements are equivalent or not at random, probably you're not going to get something which we're going to want to call an equivalence relation. Why? Because for such a rule to be called an equivalence relation, it has to satisfy these three axioms, right? The reflexive, symmetric, and transitive axiom, right? So we want to consider, first of all, if the same element comes to you twice in this guise and asks, am I equivalent to myself? Then you have to say yes, right? So each element better be equivalent to itself. And then if two elements come to you in opposite orders, well, if they're equivalent in one order, they better be equivalent in the other order as well. So order should not matter when elements are equivalent. So X is equivalent to Y if and only if Y is equivalent to X. And the transitive condition is that if an element X you decide is equivalent to Y, and then you decide that Y is equivalent to a third element Z, then you have no choice. You have to make also X and Z equivalent. Okay? And so if you imagine yourself as the equivalence relation master, right? And all possible pairs of elements of X walk up to you, and you tell each pair, you two are equivalent, you two are not equivalent, you two are equivalent, you two are not equivalent. If at the end of the day, once you've gone through all possible pairs, you've created a rule that satisfies these three axioms, then you've actually created an equivalence relation. Okay, so this is usually a little confusing, so give me a yes, no, maybe.
What does the S stand for again?
So S stands for symmetric. R stands for reflexive, and T stands for transitive. Okay, thanks, Vanessa. Somebody else give me a yes, no, maybe on the chat, just so you know I can move on. Thanks, Artie. Thanks, Berkeley. Heidi, great. Okay, so in fact, why do we introduce partitions and equivalence relations together? Well, because in a sense, partitions and equivalence relations are very intimately related, right? In the sense that if you start from a partition, right, you can give an equivalence relation. So let's look at the example that I drew, right? I can decide that x1 is going to be equivalent to x2 if and only if they belong to the same subset of the partition. Right? So having broken up X into these four subsets, U1, U2, U3, and U4, gives me a rule, a candidate for an equivalence relation. In this rule, for example, this element is equivalent to this one. The element you want is only equivalent to itself, right? And this element is equivalent to this one, this is equivalent to this one, this is equivalent to this one, and and these two elements in the U4 are equivalent. And you can check that the three axioms are satisfied, because if you take this as the rule, then, well, every element is in the same subset as itself. If X is in the same subset as Y, then Y is in the same subset as X. And if X and Y are in the same subset and Y and Z are in the same subset, then X and Z are in the same subset. And this, for this to be true, is important that the UIs do not intersect.
So is this saying, like, in a sense, partitions and equivalence relations are the same?
Exactly, yeah. They're the same in the sense that if you start from a partition, there's a natural way to come up with an equivalence relation. Here we go, right? And vice versa, if you start from an equivalence relation, so let me now draw another set X and say, let me draw some elements of X, kind of at random. And I've drawn the elements of X with different colors, and then I give an equivalence relation that says X1 is equivalent to X2 if and only if they have the same color. Again, you can spend a little bit of time later to convince yourself that the three axioms are satisfied, reflexive, symmetric, and transitive. But this equivalence relation gives me a natural way to create a partition of X. I don't know why I'm moving to create a partition of X. Namely, I'm going to subdivide X into precisely the subset of elements that have the same color. So up here, I started with a partition and I came up with an equivalence relation. Down here, I started with an equivalence relation and I came up with a partition of X. And you can, again, do a little bit of mental yoga and see that if you start from a partition, come up with an equivalence relation, take that equivalent relation and draw the corresponding partition, you come back home, right? So they're really the procedures that are inverse of each other. So equivalence relations and partitions are the same things, okay? So now, if you start from an equivalence relation, this subset you create of elements that are all equivalent, these 4 subsets right here, are called equivalence classes. Okay, so now I can answer Berkeley's question from the beginning of the hour, which is, so an equivalence relation is a rule that decides when elements of a subset, of X are equivalent. Okay. Once you have an equivalence relation, you get a partition of the set X into subsets of things that are equivalent, and the subsets are called equivalence classes. Equivalence classes are subsets of elements that are equivalent and, let me say, add this maximal. What do I mean by this? What I mean by this is that I don't want to, so if I take as a subset only 2 out of the 3 black elements, that is a subset of elements that are equivalent. But I don't want to consider that an equivalence class because there's a 3rd black element out here that is also equivalent to them, right? So this is not something I want to consider as an equivalence relation. So I say the equivalence class, as an equivalence class. So equivalence classes are subsets of elements that are equivalent and such that you cannot grow them anymore with elements that are equivalent. So there's no more elements that are equivalent to elements in that subset, outside that subset, right? So this purple set is not going to be allowed. This is not an equivalence class. Okay, this is another good moment to pause and ask you for a quick confirmation that you're still with me. Thanks, McKinley. Thanks, Sarah. Okay, so now comes the confusing thing. And now we can say, okay, well, if you have an equivalence relation on a set X, you have the subsets of X called equivalence classes. So let's consider the set of equivalence classes. Right? So again, in this example, I could say, well, I have one equivalent class consisting of black elements. So I'm going to denote it with a black dot. I have one equivalence class consisting of blue elements. So I'm going to denote it with a blue dot. One equivalence class consisting of red elements. So I'm going to denote it with a red dot. And I have an equivalence class consisting of green elements. So I'm going to denote it with a green dot. And so the set of equivalence classes in this example has 4 elements. Even though my original set X had 3 plus 4, 7 plus 3, 13 elements. Okay. So this set of equivalence classes is called quotient set and is denoted X mod squiggle, and it's called the quotient set. Okay. So the confusing thing is that when I talk about an equivalence class, I might be referring to just one element of the quotient set, or I might be referring to a subset of X. And unfortunately, this is a confusion that math decided to not resolve, right? And we have to live with it, right? So you have to understand from the context whether you're wanting to talk about an element of the quotient set or a subset of X. Another confusing thing is, what do we call equivalence classes? Well, in this case, we can call it, black, for example, because we said, well, we've decided that this is the equivalence class of all the elements that were black, and we could call this one blue, for example. But one way, now let me give it some names to these elements. Suppose that I call this A, B, and C. One way that I could talk about the element black is the equivalence class that A belongs to. Okay? Because, well, if I tell you it's the equivalence class that A belongs to, you go look up A is black, so that's black. So that's the same thing. Okay? And so because that's a long sentence to have to write every time, right, we created a notation for this, which is square brackets. So square brackets A means the equivalence class that A belongs to. And now you see what kind of the bug with this is, or feature or the bug depending, is that, well, this is also the equivalence class that B belongs to. Because B also was black, and so we have that square bracket A is equal to square bracket B, even though A is different from B, right? A and B are two different elements of X, but they belong to the same equivalence class, so square bracket A is equal to square bracket B. So the confusing thing is that one equivalence class can have many different names. Oops. Okay, glad everything is okay, Berkeley.
So I have a quick question.
Yeah.
So would an equivalence class, like with numbers, we've been using colors, is, for example, for 1, so 1 would be equal to 2/2, 3/3. Like, is that something that we
Yes.
Okay.
That's awesome. Let me finish writing the sentence and I'll come back to exactly your observations, because I was going to ask you guys that. So you prevented me. That's awesome. As many names as elements in the subset. Okay. And was that Tyler speaking?
Yeah.
So Tyler observed that we have already encountered this notion because rational numbers, right, are numbers of the form P over Q, right? But really, we have, ever since kindergarten, we have been not scared by the fact that 1 is the same number as 2/2, 3/3, 4/4, 5/5, and so on and so forth, right? So in this language, rational numbers are equivalence classes of fractions. And what is the equivalence relation? Well, P1 over Q1 is going to be called equivalent to P2 over Q2 if and only if, when you cross multiply, you get the same integer, right? If P1 Q2 is equal to Q1 P2. This, again, is a rule of equivalence that satisfies the three axioms, so that works. And if you use this rule of equivalence, you'll decide that 1 over 1 is equal to 2 over 2 is equal to 3 over 3, and so on and so forth. Okay, so that's a fantastic example of equivalence relations. Okay, and I'm 1 minute over time, but give me just 30 more seconds to introduce the projection function, so that next time you hit the ground running. Well, so there's a natural function. If you have a set X with an equivalent relation, there's a natural function from X to the quotient set, and is the function that assigns each element in X to the equivalence class that X belongs to. And the way to write this in short is assigns X to square bracket X. Right, so you go back to this example and you say, okay, if I want to create a natural function from this set X to this set down here with only the colors, well, I'm going to send all the black colors to the black dot. Sorry, all the black elements to the black dot, all the blue elements to the blue dot, all the green elements to the green dot, and all the red elements to the red dot. And I get a natural function called projection function. And the projection function is surjective. Okay, so this is the material that I wanted to introduce. In the group work, we'll work towards becoming more familiar with all of this, and also we'll want to kind of, when we wrap up, we'll want to make sure that we'll have understood this goal. Okay, Berkeley, you still okay? You have a roof over your head?
Yeah, just all my stuff got knocked off the walls, so.
Oh wow, okay, that must have been.
Yeah, it hit like on my wall to my room.
Wow.
So.
Okay. Well, glad it was just a momentary scare. Everything good with the math? You and everybody else? Okay. I think silent means good. Well, thank you all very much. Stay warm, stay safe, stay sane, and we'll see you all on Thursday. Bye, everybody.